Okay, guys, so we are into day 18 of rotational mechanics. In yesterday's class, I discussed all about rolling kinetic energy and the problems related to rolling kinetic energy, right? So in today's class, like some of the people asked me some doubts about rolling kinetic energy. Like I've discussed these kind of models, but some people have these doubts. So I'll discuss one or two models regarding that, and we go back to the instantaneous axis of rotation and the slipping topic. Okay, I introduced the slipping topic yesterday already, but just a few one or two problem discussion, and that's it. We go to slipping again. So the problem goes like this. Like I mentioned this thing on this side, it is in pure rolling. The body is in pure rolling. Like by the time it comes back, all we need to do is simply write mgh. Since it is in pure rolling, it has v and it has omega, so it will have half mv square, half I omega square, right? But if only we have what do you say, a, a smooth surface, you simply need to understand one point. Whenever you have a smooth surface, the thing that happens is, whenever you have a smooth surface, the thing that happens is, if there is no omega, there won't be any omega. If there is already some omega, the omega will stay. Omega won't change. That's a simple point. It won't change. If it is zero, it will stay at zero. If it is some omega naught, it will stay at omega naught. If it is a smooth surface. Now, in the beginning situation, there is no omega at all. But by the time this body comes down, there will be some V, but there won't be any omega since it is smooth. You getting my point? So all you need to do is mgh is the potential energy here equals to half mv square. Mgh equals to half mv square, and that is how we do it. But if only there is a problem, like let's talk about a problem where both are climbing up. A body is in pure rolling case, one case it is in pure rolling with v and omega, and it climbed to a height h, let us just say. So what you need to write is half mv square plus half I omega square equals to, when it climbed to the topmost point, it only has potential energy, so that is the maximum potential energy there. Now let's take a smooth case. Now let's give the body some v and omega. Since it is smooth, the omega won't change. That's the point. So even at the topmost point, there will be omega. The v will not be there. So when you write the energy conservation, let's write this as some h1. Okay, so it has half mv square plus half I omega square initially. Finally, also you have the same thing, half I omega square plus mgh1. Now, rotational kinetic energy stays like that, exactly like that, and you have additional potential energy. That's all. So it's just a linear kinetic energy that got converted into potential energy. And one or two persons asked a similar doubt. Just like this. I don't understand why. Some person asked a question like he didn't understand the question at all. I don't know why. So he says from h height in pure rolling, it gained a velocity v. Okay, so the question goes like, from what height, what height h1, if it is smooth surface, if it is a smooth surface, if it has to get to v only, what must be the height? It's a very simple thing. You here you write mgh, here you write both pure rolling, so half mv square plus half I omega square. You equate these two. But in smooth surface, you write mgh1. There is only half mv square. There is no rolling kinetic energy. There is no rotational kinetic energy. So you solve this problem like this. Simply put every value in there and try to find the h1 value. I don't understand why someone found this question very difficult. Aniket, what is it?
So one small doubt.
Yeah.
Here the ball is rolling on the smooth inclined surface also, right,
No,
sir?
no, 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 no. That's why there is no omega at all.
Okay, sir.
Now, remember, Aniket, just remember this point. Whenever you have smooth surface, just try to remember the omega won't change. If there is some omega, the omega remains. If there is no omega, it's like omega is initially zero. No matter what kind of problem you're solving, omega is finally zero only if it's a smooth surface.
Okay, sir.
There's already, let us say, somebody uh, put a body on the ground already with some omega and some other v, let's just say, and there is no friction, there is smooth surface. No, so no matter what happens to the body, no matter if it collides with a wall, no matter what happens, since everything is smooth, the omega remains the same no matter what.
Understood, sir.
Yeah, you get my point. If it is
Yes,
a
sir.
smooth surface, omega has to remain the same value. If
Sir,
it is zero,
so
yeah.
in that question I asked, sir, there were two options, right, sir, that the ball cannot roll on. It was one was smooth surface and flat one was inclined plane. So both options are correct, right, sir?
No, let me correct it again. Let's take two flat surfaces. One is rough, other is smooth. Now, even though no matter how you leave it on a rough surface, it will come to pure rolling. On a smooth surface, you exactly have to give that V naught and omega naught such that V naught equals to R omega naught, then it will be in pure rolling. But on an inclined surface, it has to be rough for pure rolling. On an inclined smooth surface, pure rolling is not possible. Like I mentioned, the
Okay,
V
sir.
and omega is changing constantly here. So there's someone who is changing both the values, gravity and friction. Here there's only gravity. Gravity is clearly supporting it, but there is no friction to change the omega. So that is why pure rolling is not possible in a smooth inclined surface. You get it now?
Understood, sir.
Yeah. So let's get back to today's topic. Those were the questions just asked yesterday. And I remember I was talking about instantaneous axis of rotation. So there are two ways. Like instantaneous axis of rotation is like an additional topic to understand. Okay, like whenever you have a rolling body, whenever you have a rolling body, you can tell whether the rolling body is in pure rolling or sleeping. Okay, so let's take all the three cases. I'm going to draw all the three cases here. In one case, 2v, v0. So if only we try to find the instantaneous of axis of rotation, ia over is coming right here. So we can clearly say it is in pure rolling. There's no problem there. Okay, but the problem comes when, no, there is no problem, but you can clearly tell one thing, that if the velocities are not this, like let us say somebody has this has 3v velocity, this has 2v velocity, this has also some velocity, the bottommost point also has some velocity. Now you try to find the instantaneous axis of rotation, it is coming somewhere around here outside the body. And you can also say one more thing, that compared to the ground, the bottommost point is sliding forward. Compared to the ground, the bottommost point is sliding forward. So they call this as forward slipping case. They call this as forward slipping case. And we will come back to that case. Like we'll clearly discuss the case. I'm just talking in the terms of instantaneous axis of rotation. In this situation, let us say you have a 2v, you have 0.5v, and you have 1v in the backward direction. Now you try to join all these three, and this is where you're getting the instantaneous axis of rotation. Now you can clearly see one more thing, that the bottommost point is sliding backwards compared to the ground. What do you call it as? This is called backward slipping. This is called as backward slipping. Do you get it? So this is just an introduction. Let's just say as for forward slipping and backward slipping. Let's actually get into the topic. Okay, let's not just leave the topic like that. Let's talk about the topic clearly. I'm going to talk about forward slipping for a while. Any examples for forward slipping? Raise your hands and speak. Anybody? Any examples for forward slipping? Yeah, Aditya.
The F1 car sliding over the track while turning.
No, it's difficult to understand for people. Let's talk about some easy examples.
So when we don't change gear and drive with too much speed, there Wheel rotates too much and we slip.
Why are you giving all complex examples, Zaid?
Sir, like when the car drifts, the drift is
Uh,
generated, so it
all the
slips.
guys are just giving all the super sports car
Sir, one more
examples.
example.
Yeah, that's all you can remember. So,
Yeah, yeah.
yeah.
I'm just looking for an easier example. Anybody else?
Mhm.
Sir,
Sir,
can I
like
give?
you have
Vehicle
thrown a
machine.
ball on a
Sir,
floor so
cup.
fast that it slips, sir.
Yeah, Aditya.
Sir, in machines.
But yesterday somebody gave a really good example. You might have most of you people might have gone for the bowling, not cricket bowling, the bowling, but you go for, in the malls, right? What you do is you simply take a spherical ball, you slide it on a smooth surface. Now, clearly observe this thing. You are giving more linear velocity, but you're not really giving enough angular velocity. That is when forward slipping happens. So, I'm taking this case like I'm going to write this thing as a combination of two things only. In forward slipping case, there will be huge linear velocity, very huge linear velocity. So all the points have huge linear velocity. But problem is the angular velocity that they provide is very small. The angular velocity that they provide is very small. So because of this, r omega, small r omega, very, very small r omega. So when you combine both of them in a single diagram, this is what it looks like. Let's get ready for that. I'm taking all the huge linear velocity diagrams. I mean, linear velocities. It doesn't fit there. Okay. All the linear velocities. Along with that, the velocities because of the angular velocity. R omega, R omega, R omega, and R omega. I hope you can understand this example. Huge linear velocity, but very small angular velocity. Clearly V is not equals to R omega. You can clearly see, it is clearly evident that V is not equals to R omega. So in this case, when compared to ground, the ground is clearly at rest. Compared to the ground, the bottommost point is not at rest. It is actually slipping forward. So this is called as a forward slipping case. This is called as a forward slipping case. Now, what happens when you put a body in the forward slipping? Nothing really happens. It's not like it's a crime or anything. But if only it's a smooth surface, Aniket, I'm repeating this for you. If it is a smooth surface, this has high V and very small omega. Since it is smooth, nobody is really changing anything. So it will stay like that forever. This V is going to stay like that. This omega is going to stay like that. The body is going to keep going in the same manner with the same velocity, same linear velocity, same angular velocity forever. But if only there is friction, this is where the story gets better. If only there is friction, you clearly can understand the bottommost point is sliding forward, so it will experience a friction backwards. Now this friction is like, let us say V is very high and omega is a very small value. So this friction is going to bring down the velocity V. You clearly can see, right? Since velocity is like this and omega is like this, now the friction is clearly opposing the linear velocity. Linear velocity is like this, friction is like this. But it is actually supporting, it is creating a torque, Fr torque is supporting omega. So it will bring down the linear velocity, bring up the angular velocity. So they both reach to a point V naught omega naught, where V naught equals to R omega naught. So eventually, when you have a frictional surface, eventually it will enter into a pure rolling. So that is the advantage of it. Aditya, what is it?
So, sir, this is the case when we throw a bowling ball. For initial moment, it will only slide, and after some time, only it starts rolling. If you
Exactly. In a
observe.
bowling, I have this example. I'm not sure if you have seen this thing in the website. See this simulation. Guys, what do you have as doubts?
So this was only my doubt that day. That why does it slip first and then roll?
Exactly. So initially, the omega was not given. We didn't actually give the values V and omega. We only gave V, high V, less omega. In fact, in this case, there is no omega at all. Omega is zero. So friction is going to act in the situation. He gave the friction value. Let's bring down the friction value to 0. I've just brought down the friction value to 0. Let's see if I run the simulation. Let's see what happens.
Sir, reduce the radius. It will look clear.
It's already looking clear. Does it not look clear? I don't know why.
No, sir, like the lines we can see more properly.
Okay. What difference did it make?
So now if you put friction, it will be better.
Whatever, man. So if there is no friction at all, the body just keeps on sliding the same thing. But if only I give it some friction, let's just say small friction. So on a frictional surface, now the body is on a frictional surface. It is in a forward slipping case only. Why is it in forward slipping case? Can anybody tell? Arre. Why is it in forward slipping case? Because V is very high, omega is very low, as in there is no omega at all. So the bottommost point is actually slipping forward. So the friction is acting backward. The friction will bring down this V, will support this omega. So omega, V will be brought down, omega will be increased. So there comes a point, there will be some V naught, there will be some omega naught, and at that point they will be equal and they will enter into pure rolling. Vamshi, do you have a doubt?
Yes, sir.
Yeah,
Sir,
tell me.
cylinder rolling one is
Your
slope.
voice is way too low.
Sir, cylinder rolling one in slope, it will come
Still
to
can't
top.
hear you. Anyway, let's just run this simulation first and let's look whether if it is gonna happen or not. You see, when that trace is turning brown, that is when the body is actually entering the pure rolling motion. Even in this thing, they clearly mentioned everything here. Like right at the bottom, you clearly observe right below the ball, they actually mentioned up to what point it is slipping and after what point it is erase the traces. After what point it is into pure rolling. Like clearly watch. I'm going to increase the velocity just for some understanding. You see, from this point onwards, it is entered into a pure rolling. So after some velocity, after some point, we will learn how to find these points, how to do all these things, definitely for sure. But I'm just giving you some examples. Guys, if you have doubts, you can speak. Aniket.
So what happens is omega is there and V is not there.
That is the other case, backward slipping case.
Oh, okay, sir.
Okay.
Sir, can
So
you
let's get back here. So guys, try to understand, whenever we provide high amounts of V and small amounts of omega or even zero omega, all you need to look at is the bottommost point, guys. The bottommost point, if it is sliding forward, if it's sliding backward, that's what you need to observe. If it is sliding backwards, forwards, it's a forward slipping case. The friction is acting backwards and all. So it gets really easy. I mean, like you'll clearly understand that after some point, V is very high, omega is very low. They adjust themselves so that they reach some velocities so that they get into pure rolling. Aditya, you have a doubt?
Yes, sir.
Yeah, tell
I
me.
wanted to ask, like, if they asked us in this in an inclined surface form, so can we conserve energy here now?
If it is inclined or here?
Yeah,
If it is
yeah, it's
inclined, no. There was a lot of slipping. Guys, in this case,
yes, that's
you
right.
cannot conserve the energy. Please observe the point. You
Yes, sir.
cannot conserve the energy because there was a lot of sliding in between these two surfaces. So there's a lot of heat that is generated. All that part is gone. So you cannot definitely conserve the energy. Even if it's on an inclined surface, if there is slipping, you cannot conserve the energy. But guess what? There is something else that we can clearly conserve. What is that, Aditya?
Momentum,
What momentum?
angular momentum.
Why?
Why? Because actually, here the body is in the same system, and only the velocities are getting changed. The moment of inertia isn't changing, no, sir.
You're not giving the right excuse. Anyone else?
Because the axis is not changing.
No. Anyone else has
Sir,
an?
no external force is acting or torque is
What
acting.
are you stupid? There is friction. So guys, I'm going to draw the diagram. Initially, there is high V and very small omega. After a while, it is going to enter into pure rolling. So after specific point, there is some good V naught, some omega naught, such that V naught equals to R omega naught. V naught equals to R omega naught. Okay. Now what I'm saying is I just mentioned one point that you cannot conserve the energy because there is a lot of sleeping. But I just explained it in 2 days ago, I guess. About these points, you can conserve the angular momentum. There is a reason why. You write the angular momentum about any point on ground. I'm not choosing some random. You can choose any random point. You can choose any of these points. You can conserve the angular momentum. The reason is friction is acting, mg is acting, normal force is acting. Guys, clearly observe the torque due to mg and normal force are balancing each other. So that is why mg and normal force you don't even have to consider. Mg and normal force are not I mean, like they are creating torques, but they are balancing each other. The only external force that we need to worry about is friction. And the best part about friction is, Vamshi,
Yes, sir.
what's happening here? The best part about friction, it is passing through the point that we are considering.
It doesn't affect now, sir.
No, it is passing through the point about which point you're trying to take torque. You're trying to take the torque about this point.
Yes, sir. So it will have zero
So
effect on the torque,
even
right?
friction also has no torque. Since there is no external torque equals to zero, angular momentum is conserved. I hope you all understood the point. Since that is what that I 2 days ago I clearly mentioned that about like we take the angular momentums of rolling bodies about the points which are on the ground. The reason is this: since the friction actually passes through the points, friction do not create any more torque. So the torque, all the torque due to mg and torque due to normal force are balanced, so they're gone, and torque due to friction is zero. So there is no torque, there is no external torque. So as long as there is no external torque, you don't have to worry about the external torque anymore. All you need to write is the initial angular momentum and the final angular momentum. Let us look at the initial and final angular momentums. Initial case and final case. Initially high v, very small omega. Finally some v naught and omega naught. So I'm choosing some random point. Can somebody tell me the angular momentums? Mv into r, if you remember this, L bar equals to mv into r, first linear momentum into perpendicular distance, plus I omega. Now the final angular momentum is the same thing. This is Li, this is Lf, mv naught into r plus I omega naught. That's it. You can equate these two values and you will happily find the V naught. And one more equation, we have V naught equals to R omega naught. We have V naught equals to R omega naught. We can happily find the final velocities and final angular velocities and the linear velocities. It is as simple as that. Okay, let's try a problem. Okay, why don't we let's take a value and try a problem. Okay, I'm going to take a disk. Get ready, guys. You have to do this problem. A disk with mass m and radius r. Now, it has v. There is no omega. Initially, there is no omega. So the body was only given some linear velocity. Of course, there is, I mean, like there's a frictional surface. It's not a smooth surface, frictional surface. After a while of sliding, it went into pure rolling. V naught, omega naught. I'm giving you 1 minute. Try to find the value of V naught or omega naught. Try to find the value of V naught or omega naught. I'm giving you a minute. Try, give it a try. If anybody has an answer, raise your hand and speak. I'll unmute you. All you need to do is take a point on the ground, write the angular momentum about the point initial, final, equate them, and that's all. And yeah, obviously you need to consider V naught equals to R omega naught. They don't mention it. They simply say they're in, the body is in pure rolling. That's all. Harshavardhan. Yeah.
Sir, V equal to V naught square plus 2 V naught R by R.
No, you got a very wrong, I mean, like complex answer. It won't be that complex. You'll get a very simple answer. You missed out something. Aditya, Aniket.
So V is equal to 3V naught upon 2.
So 2V
I
is equal
wanted
to
V
V
naught.
naught.
I wanted V naught. I didn't
V
want
naught is 2V, sir.
Okay, 2V upon 3, sir. V naught is equal to 2V upon 3.
maybe. I think Aditya is right. Aniket,
Sir, I got just 2V.
how can you have more linear velocity? Sharat,
Sir, root over 2 by 3 V, sir.
why are you getting root values here? I'm not
Sir,
quite.
root over.
I think they
there
have
will be
taken
square head.
energy like V square, so they
Guys,
have
did
taken like
you conserve the energies here? I clearly told you energy is not conserved. It is a momentum, angular momentum that is conserved. Shall we write L initial equals to
So
mv
3 by
into
2.
perpendicular. I'm taking some random point on the ground so that friction is passing through that. So about that point, angular momentum mv into perpendicular distance r, so mv into r plus I into 0. So there is no angular velocity at all initially. Finally, L final equals to m v naught r plus I omega naught. Let's extend the values. M v naught r, I is nothing but mr square by 2 omega naught, and on this side it is nothing but mvr. That's all. So mvr equals to this. Mvr equals to mv naught r mr into r omega naught by 2. I'm just writing r square as splitting it, okay, so that I get some easy value. Mv naught r plus mr, this is also v naught, so you get 3 mv naught r by 2 equals to mvr. mr, so I get v naught equals to 2v by 3. I hope you get it now. Now, yeah, everyone's texting me on the chat. Okay, so yeah, this is the answer, guys. Final velocity, like this is how they simply frame a question. Okay, on a frictional surface, they leave a disk with linear velocity, only linear velocity. Once it gets into pure rolling, how much is the linear velocity? This is how they simply frame this question, and you know what to do. All you need to do is simply find the angular momentum and do the question. Okay. Let us talk about backward slipping now. Can somebody tell me what backward slipping is? It is a case where, of course, you raise your hands. It is a case.
so where
So
omega
when
is
we are
more
bowling
and
in the
V is
bowling
less.
alley, sometimes it comes backwards and then goes forward.
No, not exactly.
Omega is more and V is less, sir. Here
Yes, sir.
Exactly.
initially.
So it's like very small v, but very high omega. So the small v applies to all the points as v, but the omega is causing huge r omegas at all the points. So when I combine them into a single diagram, what is happening? Let's look at the only bottommost part, okay? We don't have to write all the bits. V and r omega. This is what happens when a car suddenly takes off. You might have seen this thing in movies, or like when you immediately give petrol, immediately accelerate a car. What happens is the car immediately gets a lot of angular velocity. So the angular velocity is very high, but you don't have enough linear velocity in that situation. You don't really have a lot of linear velocity. So in this case, compared to the ground, the bottommost point slides backward. So in this case, the friction actually acts forward. So guys, remember, in backward slipping, now please remember that in backward slipping, it doesn't mean that the body is going backward. The body is still going forward only. The body is still going forward only, but because of this huge omega, the center of mass of the body is still going forward. Please try to observe that. But the bottommost point has a velocity relative to the ground into the backward direction. So this is called as backward slipping. Please observe the point that the body is still going forward only, but it's just the bottommost point is slipping backward. So in this case, the friction will act forward. And when you accelerate a car, this is the friction. This is the reason why it actually accelerates. The friction is actually making the car move forward. You please try to understand this. When you start a car, when you suddenly accelerate it, you're giving a lot of angular velocity to the car. You're giving a lot of angular velocity to the car. That angular velocity is making the car backward slipping, like the tire is slipping, the bottommost point is slipping backward. So the friction is acting forward now. Neeti and Preeti and Sumant, what's your doubt?
Sir, is this the same thing that happens when a normal tired car try to go on ice, sir? Like on
I
a
didn't understand.
smooth surface.
Yeah, exactly on a smooth surface, if only it is smooth, what happens is, like if only the surface is very smooth, what happens in a car is a car tries to give a lot of omega. There is no V. The V is very little or zero. So the bottommost point is clearly having R omega in the backward direction, but there is no friction created. What happens naturally if only there is a frictional surface, this friction try to clearly observe this friction. We already know this thing, right? The omega is very high value, V is a very small value. Clearly observe friction is in the direction of V, but friction is creating a torque which is opposite. This is Fr. Torque direction is opposite direction. So friction will oppose omega, will support V, so that they reach a pure rolling case. So in a 1 second, in a backward slipping case, this is what happens. Like the friction acts forward, it supports V, it opposes omega, and so the body get into pure rolling. So if only you are on a smooth surface, there is no friction. So there is no one to bring up V, and there is no one to bring down omega. So the car keeps on slipping there, the wheel keeps on slipping there. It will never move forward, or it will never move from that position at all. Okay. Any doubts? So bring up your doubts now. Neeti,
Sir,
So another example, like when a vehicle is trying to
I
pass
can't
through.
hear you. I can't hear you.
Sir, can you hear me?
Yeah, still
Sir,
low.
sir now.
Better. Yeah.
Sir, like when a vehicle is trying to move through pass mud, sir, it
Yes,
requires a
yes,
lot of
exactly,
acceleration, but it
exactly. Well,
doesn't
that's
have.
what happens when a vehicle is stuck in mud. The friction is not sufficient, so you'll have a lot of omega, but the friction is not sufficient for the car to move. So it creates any V, so the wheel just keeps on slipping there. Yeah,
Yes, sir.
sir,
yeah, Vamshi.
one more thing we can share, sir. When we walk on a slippy surface,
That's also good, but it's not pure rolling, right?
yes.
Yeah, so when you're walking also, it's the same principle. It's a friction that is actually supporting you move forward. It's the same thing. The car is also being supported by the wheel. So if only someone gives you a problem saying there is no smooth surface problem, okay, we can't deal with smooth surface problems. There is nothing changing in a smooth surface. I mean, we can deal with it. There's nothing changing there. So let's just leave it like that. So on a surface like this, you give a body a lot of omega, very small v, like zero v in fact. Okay, so the friction will act forward, it will support v, it will oppose omega. After a point, they get into pure rolling, v naught, omega naught. You can happily take any point on the ground, angular momentum initial angular momentum. Final, you can equate them and find the values. That's all. Aditya, sorry, Aniket has a doubt.
The small doubt here, the friction is helping the body move forward, right, sir?
Right, yeah.
So it should be like forward slipping, right, sir? Why backward?
It's about what the bottommost point is happening. Like I mentioned it clearly. The word slipping is always regarding the bottommost point. So it's all about what is happening to the bottommost point. Look at the bottommost point. It's still going backward only. I mean, like compared to the ground, the bottommost point is actually going backward.
Okay, sir.
Okay, so in the forward slipping, the bottommost point, where is it? The bottommost point. Where did it go? Yeah, in this case, the bottommost point is actually going forward. So try to remember that it's always about the bottommost point, like whether it is forward slipping or backward slipping. Okay, Zaid.
Sir, in ice skating, is it a type of slipping like forward or backward, or is it no slipping at
No,
all?
like if you're talking about rolling on ice, if it is just
Yeah,
skating on
nice.
ice, it's not even rolling, right? It's basically a
Not even
friction topic
right.
question. Okay, there is nothing related there. But if you're
Okay.
on ice surface with a car, let us say, and your car wheels are clearly only slipping, there is only high omega, but there is no V. So you're clearly having a backward slipping there. Okay, Sharath.
Sir, so we can say that friction in this case opposes omega, right?
Yeah, exactly. That's what I said in this, like right here, I said the friction brings down the omega, brings up V to reach a point where V naught equals to R omega naught.
Sir, so at any given instance, sir, if it isn't mentioned like the ball is slipping or something is slipping, so like we can use the friction's direction to find out in which direction it's slipping,
Yes,
right?
definitely. If they didn't mention anything, they have to mention something. If they mention that V is greater than R omega, it's a forward slipping case. So definitely friction is acting backward. If they mention that V is less than R omega, it's a backward slipping case. So friction is clearly acting forward. Or if they mention these, you can deduce these. It's your call. Like depends on the problem. Okay.
Okay, sir.
But you need to understand. You just have to understand the thing that no matter what is the case, if the body is not in pure rolling, to bring it into pure rolling, the friction is sometimes it's all the friction is always doing its work by supporting V and opposing omega some cases. In another case, opposing V and supporting omega, and the final job for it is to bring the body into pure rolling. And to solve the entire problem, all you need to do is not the energy conservation. Remember this point. You should not conserve the energy. You should simply conserve the angular momentum, and the problem is done. The topic is done. Okay.
So
Yeah.
what about when the body isn't slipping, sir? Then the friction will be in the backwards direction,
No,
right?
there won't be any friction if the body is not slipping at all. Did,
Only rolling, sir.
did you not observe one thing? Did you not observe one thing? Uh, oh, come on. Like you need to observe. You need to observe one difference. There are cases where we're talking about A and alpha. There are cases where we're talking about P and omega. Okay. Oh, it went to some other dimension.
The beginning of rolling.
Yeah, yeah. So there are some cases we are just talking about V and R omega. We are talking about a smooth, like horizontal surface, let's just say. You've given such that V naught and omega naught is already such that V naught equals to R omega naught. Okay. The body is already put into pure rolling. You know the direction of friction? It is zero. Why do you need friction there? If it is a forward slipping case or a backward slipping case, then you need friction. Now, in all the problems that we discussed yesterday or day before yesterday, there was always friction. But why do I say zero? In all the problems that we talked yesterday, there was some external force, constant external force. There were linear and angular accelerations. That is why there must be some friction always. I hope you're clearly seeing the difference. And there is
Yes,
some
sir.
external force, there must be friction so that the V constantly increases, omega constantly increases, V is constantly increased by this, omega is constantly increased by this. So in the case of linear and angular accelerations, yes, you always need friction. But when you're talking about a constant V naught and constant omega naught case, when it's already balanced, When they're already balanced, you don't need any friction. If they are not balanced, then you need friction. Sharath, is it clear now?
Yes, sir. Clear, sir.
Yeah, that is a difference. That is an important point. Like, please try to observe the points that these cases and these cases were different. When you applied force, the friction must be there because V is increasing, omega is increasing. So friction must always be there. Aniket.
Thank you, sir.
Sir, in the second case also we can do without friction, right? If we are applying at that
Right
specific point
specific
where,
point. Yes, exactly.
yes, sir.
At that right specific point, if you're applying, yes, you don't need friction. But that's a special case. Like, but you need to understand this. In that special case, what's happening is this friction itself is providing V and is also providing omega exactly, like according to the proportions. When you're applying it the right point, the friction, the force itself is providing both the values. So that's why you didn't need friction there. If it's any other point, you definitely need friction. So like even in this case, inclined surface and these are exactly the same things. Even in inclined surface, there is always an A and alpha. Why? There is F. There is definitely there is some F. So inclined surfaces belong to the second case only. Like try to remember this point. Sorry, try to remember this point that inclined cases and external force cases are same. Like they are completely related. These cases are like, see, those are the happy cases. Already V naught and already omega naught is properly given. And if they're not given, the friction will take care of it and bring them into equal V naught and omega naught. You know, like even if you didn't give V naught and omega naught properly, the friction will bring them into V naught and omega naught, and they won't change from this point. They will stay constant and they will just move with the same V naught and omega naught. That is the important point. Once they get into pure rolling on a horizontal surface, friction is zero. You don't need friction anymore. They will just keep on going with the same V naught and omega naught. Okay, so yeah, there's a lot. It's a lot to process at once. You watch it. You watch this class again. It will make more and more sense to you. Aditya.
Sir, once can you slide the image down?
Yeah.
Sorry, sir. I meant up. I meant up. Sorry.
Okay. This or more?
Yes, sir. A bit. Yes, yes. Stop,
Yeah.
sir. Here
Yeah.
only, sir. Like, what if after bringing to this pure rolling, sir,
Mhm.
I immediately stop both of them? Like I applied brakes.
Okay. Like so, you definitely applied some external force. Okay.
So now, if how should I do the problem next? Like, if it is like I immediately stop both of them.
You do the same thing. Torque due to that external force.
Okay, okay, okay.
You find alpha. You find A. You do all the math.
Carry away with the direction.
Yeah. What?
No, I thought direction is different, so something different will happen.
No. It's the same thing.
Yeah, that was my wrong intuition over
Yeah,
there.
yeah. It's the same thing. Okay.
Okay, sir. Thank you, sir.
So yeah, that brings us. This whole idea brings us to one last idea. This is actually not the last. Oh, I'm sorry. I forgot to discuss this model. What happens when somebody gives a V like this and omega like this? Interesting. Anybody? You might have done this thing to the coins on a carom board. We've all have done that, right? Like
Sir, we have to consider two cases, sir.
So
One
same
is
thing in
where V
opposite
is greater,
direction,
one
sir.
is where omega is greater.
no, that's a good one. Like try to remember, try to understand this case. We used to do this thing with the carom coins. You push it forward, but you give an angular velocity which is in the backward direction. So when you do this, the coin might end up in two different cases where it might get some V1 omega 1 with forward rolling case, or it might even end up with V2 omega 2 in a backward rolling case.
So after a while it will come back.
No. If you provide a high amount of V but less omega, it'll actually end up in case 1. If you provide less V but high omega, it'll end up in case 2. It depends on what you're providing. Now, but no matter what you're providing, the problem is dead simple. What do? You take this point, try to write the angular momentum about that point, and the problem is over. That's all. But you need
So one
to
small doubt.
yeah.
So sometimes it goes forward and then turns and comes back, right, sir?
No, that's
Because
what
of the
happens. Like it goes. How do you end up in this case? You go forward and you stop at some point. So the V is dead, but the omega is still not dead. So because of the backward omega, the body will start rolling in the backward direction. But in this case, when the V is more, the omega will die soon, but some V is left. So because of that, it'll go for slipping in the, sorry, it'll go rolling in the forward direction. You don't have to talk about all these cases. It's very simple. Take this point, try to write the angular momentum. Be careful about the directions. When you write it, MVR minus I omega, MVR minus I omega initial. I'm writing the angular momentum of this MV1R1, MV1R plus I omega 1. I'm writing the angular momentum of this minus MV2R minus I omega 2. I hope you are understood. So you equate it to these two in one case, and in another case you equate these two. No big deal. You will definitely get all the answers. In fact, if you look at this quantity, it's a positive quantity. This entire quantity is positive. It'll end up in case 1. If the entire quantity is negative, you'll end up in case 2. I can even tell you that. Aniket.
So one small doubt, if omega is like too much and V is too small, can it happen like it goes forward first and then comes back and again slips
No,
because
no,
of
no, no.
omega?
It won't slip. It'll once it gets into pure rolling, nothing will happen for sure.
Okay, sir.
Okay. So guys, there is a problem in H.C. Verma where he does this. You can actually tell in which case will it end up, whether it is case 1 or case 2, just by looking at the initial angular momentum. If the total initial angular momentum is positive, it will end up in case 1. If the total initial angular momentum is negative, it will end up in case 2. You give it a try, you try to do the problem and you'll get the answers, which is quite an interesting one. But I'm not talking about that one. I'm going to bring the topic to end with this question. They talk about impulses. When you're giving an impulse, you're immediately giving some V and you're immediately giving some omega. So if you give the impulse at that right position, what is that right position? For disk, it is R/2. For ring, it is specific. There are specific values, right? Let's just say it is disk. The value is R/2. The value is R/2. If only you give the impulse at this position right away, the V naught and omega naught it achieves is actually V naught in this form only. Like the V naught, the omega naught that you will give, actually it is the right values for V naught equal to R omega naught. So it immediately gets into pure rolling. If only you don't give it at the right point, it might gain some what? So because of this impulse, it might gain some V1, it might gain some omega 1. They won't be in pure rolling, but because of friction, after a while, they get into pure rolling. This is the case. There are some problems like this. Look at these impulse problems. It's a very simple case. You need to understand. If you give the impulse at the right position, they immediately tend to get into pure rolling. If you're giving it the wrong position, they get some V1, some omega 1. The friction will come into act and bring them to V0 and omega. If there is no friction, they just stay with these values, V1 and omega 1. They just go on with those values forever. Okay. So all these forward slipping, backward slipping, and fun cases are like this. We can talk about this for maybe 20 more days. But I'm going to end this today. I don't want to drag it a lot, but it depends on you guys. If you simply drop it right here, yeah, you only you learned a very little amount of it. But if only you want to take it further, first complete these questions, complete the questions in DPP. There are tons and tons of books where you can practice. Trust me, you can practice for a year and I can give you a question from rolling mechanics, rotational mechanics. You won't be able to solve it. I've just talked about this question. Check this, 85. That is the question that I just talked about. Aniket.
So for that DPP, can you just give solutions? It will
No.
be very easy.
So I'm highly against solutions. Solutions, like practicing with solutions is like, I can't give a right comparison, but when I find a right comparison, I'll definitely text you or I'll tell everyone the same example, taking you as an example. Okay. It's a very
Okay,
bad
sir.
thing. You shouldn't have solutions in the back. Oh, that's
So
a
I
very
always have H. Verma solutions while
Nope.
solving it.
Don't have solutions with you. Yeah, I'll meme it. I'll make a meme about it. I even have a meme about it. Like I made a meme about it. Go check it on the Instagram page. I even made a meme about it. I remember that. Aniket, just wait for you. Like just wait a minute. I'll show it to you in the class itself.
Okay, sir.
Vamshi,
So
what is
after solving all the
Sir,
ones which we didn't get, what's wrong in just seeing them, sir?
No, 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 no. You should talk to friends. You should talk to teachers. Get an idea about it. Aniket, what is it?
sir, me, sir.
Oh, Vamshi, yeah.
Sir, the cylinder is rolling from the slope that you can say, sir, for forward rolling.
Come again?
The cylinder is rolling from a slope, sir.
Uh huh.
That example, this example will come, sir.
When the cylinder is rolling in the slope, yeah, it's like an external force is there. So there must be some friction and all.
Yes, sir.
Okay. Yeah. Aniket, do you see the meme for you?
Yes, sir.
Yeah. So live with that. That kid is
Okay, sir.
probably you when you were younger. So that's it, guys. That's it for today. Aditya has a doubt.
Sir, not in doubt totally. I had one request, like if we extend it to 1 week more for practicing, can we do that?
I'll see. I'll see according to the schedule that
Like
we
if
have.
we can HC Verma complete,
That's
we'll
what I'm
try.
saying. That's what I'm saying. I'll look into it. If our schedule is flexible, I'll try to extend it. Otherwise, I won't. Okay.
Okay, sir.
Right. So guys, if you have more doubts, I have some more somewhere else to go. So if you have more doubts, text me. We'll discuss them. And tomorrow we'll have a doubt session. Like I'll discuss all the doubts. So before the class itself, send all the doubts that you have. I'll discuss all of them. All right. Thanks so much, and bye bye.